Hi, it's time for another math easy solution. Time to discuss further into integrals, and now look at integrals and average value. Basically, show how to find the average value of a function using integrals. Basically, it is easy to calculate the average value of a finite amount of numbers. For example, if you had y1, y2, etc., all the way to yn, then the average, or the y average, is going to equal to the summation of all these, then divided by the total number. So y1 plus y2 plus etc. all the way plus yn, and then we divide this by n. Yeah, but in this example, this is basically a finite number. But what if we had an infinite amount of numbers? For example, we were to compute the average temperature during a day if there's infinitely many temperatures are possible. For example, if you had a function like this to graph out the temperature during the day, this is time, this is going to be your temperature in degrees Celsius. Let's say it goes below 0 and then it rises something like that. So let's say it rises up to, what is it, 20 degrees Celsius right here, and it's at 0. So how are we supposed to find the average of the temperature throughout this whole for the day or whatnot? For example, if this is 24 hours. I will get to that in a bit, but basically, if you were to guess what the average temperature is, we could probably just draw a line roughly somewhere here that kind of represents the most likely average, and we'll call this T average, or average temperature. And this one we just guessed, but it should be somewhere along that line. Yeah, but now to calculate this exactly well, we could basically use the concept of breaking up the function into many parts and summing to infinity and writing as an integral. Basically what I've done in my previous videos on integrals and areas, and basically defining integrals as an area. So for example, if we had a function like this, there's our x, there's our y-axis. So let's just say the function looks something like that. This is our f of x. Yeah, and we wanted to know what the average area was between this point right here, which is x equals to b, and x equals to a. Now to find the average, or the f average, or f of avg, we basically will do the same thing we've been doing before. We would first estimate what the average is by first drawing a bunch of rectangles. Let's just draw one right here, and we'll use we'll use just any point like this that connects there. Yeah, actually in this example, we'll just try to make it roughly in the center, actually, something like this. So if we were to draw a bunch of rectangles, and where it touches through the center, it doesn't have to be in the center, it could be pretty much anywhere. Yeah, but in this example, I'll just use the center right here. So yeah, basically, so now we have in this case 5 rectangles. So if I call this xi right here, then at this point right here, this is f of xi. So now if we want to find the average of these 5 rectangles, or let's just assume there's a generic n rectangles right here. Let's go n rectangles. Then we can roughly guess what the average of this function here from x equals a to x equals b, as, let's go, f average right here, is roughly equal to, now we're just going to write this is going to be f of x1 plus f of x2 plus etc. all the way to f of xn. And like before, we would divide this whole summation by n, or the number of rectangles. So that is how our average function looks like. But in this case right here, we could write n as a function of the width of each rectangle. So this is delta x. So now delta x, we'll bring that over, delta x equals to, yeah, this width is going to be, well, the width, it's all the same width, so yeah, the width will just be, well, this length divided by this n. So we'll go b minus a divided by n, which is basically going to be, you're taking the width, so which equals to the width total width divided by, well, divided by n, and then you get individual widths, which is going to be that. So now we could solve this n in terms of delta x. So this equals 2, move this over this side, and this underneath, so we'll get b minus a over delta x. So now we could plug this into there. So we get f average is roughly equal to, and this summation right there, we could actually write that as a summation, yeah, and write it as summation from I equals 1 up to n of f of xi. Now we're dividing this out by, well, b minus a divided by delta x. So now we can move this delta x on top. So this equals 2, yeah, this side equals 2 now. This is 1 over b minus a delta, this is the sigma, I equals 1 up to n f of xi delta x. So you could put the delta x out of it, or I like to keep it inside, because we could soon transform this into the integral. So it doesn't matter if it's outside, inside. I take this one out, it's going to be always constant, and we don't need this for the integral in terms of putting it inside. So basically we have this now, but this again is an average. And like I've shown before, for when you deal with integrals, if you basically break this down, instead of this finite number, if we go infinite amount of rectangles at infinitely small, we get basically f average is going to equal the absolute value of it, yeah, the actual value of it is going to be equal, well, it's going to be 1 over b minus a times by the limit, yeah, the limit as n approaches infinity. So now this constant could be inside or outside, doesn't matter, it's always going to be the same. So now we go of I equals 1 up to n of this f xi delta x, and now we could write this as an integral. So this is equal to 1 over b minus a integral now, because this is just a Riemann sum like I showed in my integral proof video. This is from a to b of now f of x times it by dx. And this f of x, we're not including the I, because when it becomes really, really small, it doesn't matter if it's in the center point, the right or left, it's always going to be pretty much the same, because you get smaller and smaller. And also this dx is infinitely small delta x. And there is basically our average, yeah, our average function. Yeah, or our average of basically just any function, even if you have infinite amount of data points. And now one final note: for a positive function, we can think of this average as basically the area, the total area divided by width, which equals to the average height. For example, if you had just a positive, let's just draw this like that. So this is a positive function, this is y, this is x, and you're trying to find out the area from a to b, so I mean the average value. So we know that this whole thing is going to be the area, so that is the area. Yeah, and let's say this is our f of x right here. So the average height is going to be somewhere in between like this. Draw it in red. So now we draw this down like that. This is our average height. Height average, and so now this area right here is equivalent. So this area is basically an equivalent rectangular area of this one. So these are both the same as this one, and now we have our width right here. Yeah, so all we're doing is basically finding an average height or a height that when you multiply by w, or the width, you get the equivalent area as you would if you just to take the integral underneath the curve. That's because, well, yeah, this part right here, this is just an area, and this b minus a, that's just, well, that's 1 over width. Well, yeah, and anyways, that's all for today. Hopefully you'll learn from this video. In later videos I'm going to do some examples and also go over the mean value theorem for integrals. Anyways, thanks for watching, and like always, you could download these exact notes in the link below, and thanks for watching, and stay tuned for another Math, easy solution.